Hello students, and welcome to my video seminar on Markov chains. So what is a Markov chain? A Markov chain is a model used to describe the random probabilities of some change in state. A Markov chain's probability is dependent only on the current state, unaffected by past or future states. Markov chains can be used in a large number of fields with random variables involved, such as market share, bank loans, and even Google's PageRank system. So to begin, let's start with an example to introduce the ideas and terminology associated with Markov chains. On your screen, you should see this example I've made. You can pause the video here to copy it down or to read it. So first, I'd like to represent this situation in a diagram. The letter A means with the company, and A' means not with the company. This is what's called a transition diagram. This shows both the current states, represented by the bubbles, and the probability of what their next state will be, dependent on their current states. For example, 80% of those initially with A stay with A, and by deduction, that means that 20% move to A', and 30% of those initially with A' will move to A, and again by deduction, we can determine that 70% stay with A'. To actually use this information shown in the transition diagram mathematically, we denote it as a matrix. And we can essentially think of it as a table comparing the current state, the next state, and their associated probabilities. We call this a probability or transition matrix. For example, just like the transition diagram, 80% of those initially with A will stay with A. This is represented by the first entry in the probability matrix. However, without any other information, the probability matrix can't really be used for anything. So this is why we put the initial percentage of market share into matrix form. Again, this can be thought of as a table showing the initial distribution as a percentage. This is called the initial state distribution matrix or initial state matrix. Therefore, using matrix multiplication, the percentage of market share after 1 month can be found. For this calculation, the initial state matrix tells us the amount in the current state to determine the amount moving to what state. For example, A's market share will be 80% of the initial 30%. As well as 30% of A''s initial 70%. This follows matrix multiplication. So as you can see, after we apply the probability matrix to the initial state matrix through matrix multiplication, we can find that after initially starting at 30% market share, A's new market share is 45% after 1 month. This is called the first state matrix, denoted by S1, and is formatted the same as our initial state matrix, with A on the left and A' on the right. So now you're probably wondering, what about after 2 months? Because we're dealing with Markov chains, all that matters is their current state, which is now our first state matrix. By applying the probability matrix, we can solve for our second state matrix, S2, in the exact same way. However, because we already know what S1 equals, we can substitute that into our equation and solve for the initial state matrix and applying the probability matrix twice. You can check this on your CADs by storing the matrices. This can be generalized into a formula to find the nth state matrix. So by applying this formula for a greater number of periods, we see that after more and more months after releasing their product, A's market share appears to slowly approach 60%. To test this, we use this matrix S, which is what the market share appears to approach over a long period of time, and multiply it by our probability matrix. And quickly, you'll notice that no change occurs when the probability matrix is applied. We call this matrix S a stationary matrix, and the Markov chain is said to now be at steady state. Additionally, as n approaches infinity, p to the power of n is called a limiting matrix, denoted by p bar. This can be multiplied by the initial matrix to find the stationary matrix. So now let's look at what's called regular Markov chains. Regular Markov chains are useful because they all have a stationary matrix. A Markov chain is regular if some power of its transition matrix P has all positive entries. We already know that in our last example, that probability matrix was regular as it had all positive entries, and we have already found its stationary matrix. So, let's look at a matrix that is not regular. This probability matrix P has entries of 1 and 0. Remember, 0 is neither positive nor negative, but maybe some power of P will be all positive. However, in considering powers, it's clear that they are just switching places, and this makes sense when considering the transition diagram. Therefore, this Markov chain is not regular and will not reach a steady state. Now we know what a regular Markov chain is, we can find the stationary matrix specific to a probability matrix with the equation S times P equals S. So here is another example. Again, feel free to pause the video here to read it. From our probability matrix, we can see for people who initially play guitar on the top row, 40% will continue to play guitar, 30% will move on to vocals, and 30% will move to drums. To find the distribution after a long time, we simply find the stationary matrix. We can use the equations shown before to solve for the stationary matrix, using matrix multiplication to develop three equations, and since these numbers are a percentage, a fourth can be made by solving SA plus SB plus SC equals 1, and these can all be solved in CAS as a system of equations. After a long time, 30% of students will play guitar, 27% will do vocals, and 43% will play drums. You notice that the stationary matrix only depends on the probability matrix. It doesn't matter what the initial state matrix was, the values will always approach this number. Now let's talk about absorbing Markov chains. A Markov chain is called absorbing if it has one or more absorbing states, and it's possible to transition from any non-absorbing state to an absorbing state in a finite number of steps. Think of them like black holes. If there's only one absorbing state, eventually everything will end up in that state. But if there's more than one, they fight over it. A little trick you can use to recognize an absorbing state is if there is 1 across the diagonals and the rest of the entries in the row are 0. In the example on the screen, A and D are absorbing states and B and C are non-absorbing states. However, not all the matrices that have an absorbing state are absorbing Markov chains. For example, in this matrix, A and C simply swap around even though B is an absorbing state. So this won't approach a stationary matrix. This makes sense when considering the transition diagram. So now let's talk about what's called standard form. Standard form allows us to easily find the stationary matrix, and also has some interesting features. Standard form is essentially just reordering the matrix to form 4 submatrices based on whether they're absorbing or non-absorbing states. The example on the screen is for a 4x4 matrix, except this could be expanded for a 6x6 or even larger depending on the amount of absorbing states and non-absorbing states. Here is an example which is widely used in banking to determine the condition of a loan after some period of time. By first recognizing the absorbing states B and F, this matrix can be put into standard form, ensuring that all the entries line up with the original matrix, so it represents the same information. By reordering the rows and columns, the matrix forms the 4 submatrices: the identity, the zero matrix, and the matrices R and Q can be recognized immediately. Now that we have our matrix in standard form, we find the limiting matrix for it, and we can easily see what percentage will end up in each of the absorbing states. So to find our limiting matrix, we must first find the fundamental matrix. We do this by applying the formula F equals I minus Q to the power of -1. This can be found quickly on the CAS, however it doesn't give exact results like this. Next we can find F times R by simply using matrix multiplication. Now we can interpret the limiting matrix to see what percentage of accounts that begin in good or risky end up in which of our absorbing states after a long period of time. 23% of accounts initially in good loans are eventually classified as a bad loan, 77% of accounts initially in good loans are paid in full, 80% of accounts initially in risky loans are eventually classified as a bad loan, and 20% of accounts initially in risky loans are paid in full. We can use the fundamental matrix determined earlier to determine the average number of periods it takes for a loan initially in good or risky loans to reach an absorbing state. We find this simply by taking the sum of the row corresponding to the initial state we are interested in. Remember, these are averages and don't have to be whole numbers. For good loans, it takes approximately 3.77 years to be out of the banking system, and 2.64 years for a risky loan. Thanks for watching my seminar, and be sure to check out the extra questions to check your understanding.